Hello and welcome to my talk on a solution method for mixed integer convex multi-objective optimization problems. And the method I'm going to propose to you will avoid to scalarize the problem first, but no worries if you're not yet familiar with multi-objective optimization. I'm going to give to you a short introduction to the topic, and I'm also going to explain what a scalarization is. The talk is based on joint work together with Marianna de Santis from the University in Rome, Julia Niebling, a former PhD student of mine, and Stefan Rocktäschel, a current PhD student of mine. So multi-objective optimization, that means that we are optimizing several, here for instance, m objective functions at the same time. Here we are always minimizing, we have some feasible set. And in general, there is not one feasible solution which minimizes all objective functions at the same time. Instead, we need a new optimality concept, which is known in the literature as Pareto optimal solutions or address Pareto optimal solutions. We will call them here efficient solutions. And efficient solutions are feasible points such there exists no other feasible point which satisfies all objective functions as good and which is strictly better with respect to at least one of the objective functions. This means you cannot improve one of the functions without worsening of the value of at least one of the other objective functions. And we can also write this by using such a set notation here with using an ordering cone. And you can see here the definition is fully in the image space. I'm going to show to you an illustration on the next slide. And the image points, the images of efficient points will be called non-dominated solutions. And in general, we will have an infinite number of non-dominated solutions to an infinite number of efficient solutions. And this is a huge difference to the single objective setting. There, in case your problem is solvable, you will have the optimal value, a smallest optimal value. But here we have a whole set of optimal values, which are all vectors in Rm and the m-dimensional space, which are not comparable, which are non-dominated solutions. And in general, we want to find all of those non-dominated solutions. This is quite often not possible. Then we aim for a representation of the set or for finding approximation or an enclosure of the set of non-dominated solutions. And here's an illustration. So typically we have an illustration in the image space here for two objective functions. This might be some image set of all feasible points of some non-convex problem. And here is a definition again. And here the orange set is the set of non-dominated solutions. So these are the images of efficient solutions. And as you can see here, you cannot improve one of the functions without worsening one of the others for all of these orange points. So we will try to find those, but now for a mixed integer convex multi-objective optimization problem. So as before, we assume to have m objective functions, and we will assume that they are all nicely convex. We have convex constraints, we have a box constraint, so all feasible points are contained in some box. And we have here some integrality assumptions, some integrality constraints. So some of the variables are allowed to take integer values only. And of course, the whole problem, the whole difficulty is here in this integrality assumption. And you're already familiar with that single objective mixed integer problems are difficult to solve, but at least for some very specific situations, they are not difficult at all. And let's have a look at such a situation. For instance, if you have only one integer variable and this variable is even binary, so it can only take the values 0 and 1, then you would not say that your problem is difficult to solve, because what you would do is you would just fix your variable x1 first to 0 and then to 1. Then you have two convex single objective optimization problems. You solve those problems, have two optimal values, you compare those two values, and the smaller value of both is the optimal value of your original mixed integer nonlinear programming problem. And now let's add just one additional objective function. So say the same situation, one binary variable, but two objective functions, and it gets immediately complicated because now you would have to solve a convex multi-objective optimization problem with an infinite number of non-dominated solutions, so an infinite number of optimal values, and this is in general not possible. You can only find representations, enclosures, or similar. But let's assume for a moment you would in fact be able to solve these problems here exactly, then still you would in the end to have compare sets of non-dominated solutions to find the overall non-dominated set of your original mixed integer optimization problem. So this is illustrated here, two possibilities of an outcome. So x1 equal to 0 means you have fixed your binary variable to 0, and then you study a convex optimization problem and you obtain this green set here as outcome as non-dominated set. So these are your optimal values, and this orange line here is the orange curve is the output, the non-dominated set of your problem when you fix the binary variable to 1. And the overall non-dominated set for your original mixed integer problem is here, the part which is to the lower left. So you have calculated these parts here without using them. So this was some kind of waste of effort. But what is more, what you can see here is that both integer assignments contribute to the overall non-dominated solution set. While in single objective optimization, you're used to that as soon as you have what is called an optimal integer assignment, you're done. So as soon as you found an integer assignment which delivers to you the optimal value of your mixed integer problem, you're basically done. But here it can happen that several integer assignments contribute to your overall non-dominated set, and that you need to know all of those, like here in the setting on the left-hand side. On the right-hand side, it's in fact only the integer assignment x1 equal to 0, which contributes to the overall non-dominated set because it dominates the orange curve. But here we have had a waste of effort because we had to calculate at all points here on the orange line which are not used for the overall non-dominated solution set. So this makes it more complicated. And now I want to explain to you what a scalarization is and why I would not say that one should scalarize here. Scalarization means just the replacement of the original problem by a single objective parameter-dependent problem, and then you solve this replacement problem. And very well-known method for that is a weighted sum scalarization, where you take non-negative weights, W1 and W2, and you minimize such a function. And this is the same like moving a line in the image space to the lower left. And the steepness of the line corresponds to the choice of the weights. And here we have dots, which as image set of our multi-objective problem, which looks like a purely integer problem, but you can also think of it like a mixed integer problem by thinking that these dots are here small, tiny little sets of points. And let's have a look on this orange dot here, which is clearly a non-dominated solution because you cannot improve one of the objective functions without worsening one of the others. But no matter how you choose the weights, no matter how steep your line is, you will never be able to recover that point. You will only be able to find points which are on the convex boundary of the convex hull of your image set. And for that reason, you can see here, weighted sum is not a good idea in the mixed integer setting, because mixed integer means non-convex, and for non-convex problems, you should never use the weighted sum approach. So another well-known scalarization is epsilon constraint scalarization. There you minimize one of the objective functions and put the other to the constraints, like it's done here with an upper bound epsilon. And here we have an illustration of a mixed integer problem where it looks like we have 4 integer assignments, and the green curve here is now the non-dominated set which we want to find. And when you choose different upper bounds epsilon, you might find different points here on the green curve. But of course, if the situation looks like this one here on the right-hand side, and I could even move this set here on the right-hand side even farther away, then we have here huge gaps. And this makes it difficult to choose the upper bounds epsilon. And this gets even worse in higher dimensions. So if you have more than 2 objective functions. So this is also a difficulty here. And what is more, if you want to guarantee a certain quality of your representation of the points found, it might be difficult to decide how to choose these upper bounds epsilon. So these are all the difficulties when choosing a scalarization approach. The weighted sum is not a good idea. Epsilon constraint scalarization has difficulties. And I would like to note something else. When you make an epsilon constraint scalarization, so you solve problems of this type, they are still mixed integer problems, single objective, but still mixed integer. And those problems are still not so easy to solve. They are solved, for instance, by a branch and bound method. And you would have to redo that for all upper bounds epsilon. And so many mixed integer problems have to be solved, which are all quite similar from the structure, but you're not reusing the structure when you solve the next problem. So for that reason, we decided to develop a direct solver for our mixed integer optimization problem, which we are going to call MOMIX. And I'm going to present to you the basic ideas. It will be a branch and bound method with a branching done in the decision space, in the pre-match space. Of course, we need upper bounds, which will be just images of feasible points. And for the partitioning of the boxes, we will use branching rules, which I'm going to explain on the next slide. And then for discarding subboxes, we will rely on relaxations, convex relaxations, where we ignore the integrality assumption, the integrality constraint. And we are also going to use something like an outer approximation of the convex hull of the image set. I'm using the following notation. Whenever we have a subbox of our original box B, I will call it tilde B. And if we only consider the convex constraints, I add here a G. If we consider the integrality constraint only, I will add here a Z. And considering both means just that we restrict our original feasible set to our subbox tilde B. And here is now our branching rule. And typically, in general, for single objective mixed integer optimization, you would always split with respect to the integer variables. This is because you're used to that as soon as you have your optimal integer assignment, you are done. You only need to find that. But as I've explained to you in multi-objective optimization, it can even happen that all integer assignments contribute to the overall non-dominated solution set. And for this reason, it might happen that for some problems, it might be better to split with respect to the largest edge. And only in case this is not unique, we are taking the integer variable for splitting. So we will study in our numerical examinations both branching rules, and it will turn out that it depends on the problem considered which of both is better. Obviously, it depends on whether a lot of integer assignments contribute to the overall non-dominated set or not. And for discarding now, you're used to that you need upper bounds on your optimal value. And here now, in the multi-objective setting, the upper bounds are lists of points. Images of feasible points can look like these green dots here, and we will call those provisional non-dominated solution sets. So we will always take those which are more to the lower left. And they describe such a gray part here. And in the gray area, all is dominated by one of the green dots. So all in the gray area is worse than one of these points here, the green points. And it turns out that even more important than these provisional non-dominated solution set is the set of what we call local upper bounds, which are the crosses here. They are easy to calculate in 2 dimensions, but complicated in higher dimensions. But luckily, algorithms exist for that by Glamrod, Lacour, and co-authors. They have proposed algorithms for doing that, for calculating those. And in fact, we will have to check about the position of these local upper bounds. And then we will do some relaxations, like you can already see here. We ignore the integrality constraint, and we will check if this relaxed set is contained in the gray part or not. And for doing that, we will have to check if the local upper bounds are contained in this relaxed set plus the ordering cone or not. And then it can look like this situation here. So we have ignored the integrality constraint. We have our local upper bound P, and we check if it's contained or not. For doing that, we have to solve a convex single objective optimization problem. Then we obtain Lagrange multipliers, which deliver to us immediately such a hyperplane here. And here in this setting, we could discard our subbox tilde B because it will for sure not contain any efficient solutions. But of course, it could happen that the situation is like this one here. Still, we would be able to discard our subbox because even the convex hull of our original problem restricted to the subbox tilde B does not contain the point P. but it's hard to verify that. And for that, we use a sufficient criterion. We move this hyperplane as far as possible till it touches the convex hull. And if this is on the right-hand side of our point P, it also works in higher dimensions, but here in the illustration, it looks like it would be on the right-hand side. Then we can discard our subbox. And if this is not the case, we have to continue with our branch and bound algorithm. And when we want to move this hyperplane, we have to solve a mixed integer optimization problem, a single objective mixed integer optimization problem. And when we do that, we call our algorithm MOMIX, but we also started to avoid doing that and to have to solve a mixed integer problem. And then we call our algorithm MOMIX Lite, which just means that we are not doing this additional discarding test here, and only the lighter version you have just seen on the slide before. And we are going to evaluate in the numerical experiments which one is more promising. Because, of course, this one has a better discarding test, but it takes more time to evaluate this discarding test. And our algorithm provides also something with a guarantee, what we call a tunnel. You can see an illustration. All the dots are obtained by the algorithm. And for the tunnel, we need these crosses on the slides before, the local upper bounds. We need the images of the feasible points and some Lipschitz constant and some delta parameter. And we can show that the non-nominated set is contained in this tunnel. And now I'm coming to the numerical experiments. And first we studied the impact of the branching strategy. So we have had two branching strategies. And here, for this instance, you can see that there is no difference. So here the gray curves are obtained just by a pure discretization of the problem for illustrating how the image set looks like. And only the black dots come from our algorithm and are the output of the algorithm. And you should see that there is no difference, hopefully. And here is the illustration of the branching strategy, the result of the branching strategy. And we needed a similar number of branching in that setting here. But for other instances, we have been more successful with either the first or the second branching rule. So what you can see here is branching rule number 1, branching rule number 2. This is MOMIX, which means that we did this additional discarding test, which required to solve a mixed integer optimization problem. But we only did this for quadratic instances, and then we used Gurobi for solving the subproblems. And MOMIX Lite means that we just solved convex single objective problems, and we did not do this more advanced discarding test. Both branching rules here, scalable test instances, here the number of integer variables, here the number of continuous variables. And you can see that for some instances, branching rule number 1 was better, and for others, branching rule 2. But overall, always it was better to spend the time for making the more advanced discarding tests and using MOMIX instead of MOMIX Lite. Here you can only see results for the quadratic setting, but we also did some calculations for non-quadratic objective functions. And I'm just presenting to you some additional figures here. For instance, this on the right-hand side, it have a non-quadratic objective function. And here on the left-hand side, you can see that our algorithm also works for more than 2 objective functions. And all details can be found in our paper here in SIAM Journal on Optimization. And you're welcome to ask questions if you have later on in the discussion part of this series, of this conference. Thank you very much for your attention. Have a good day.